Assalamualaikum, selamat sejahtera to all students. So we are still in chapter 3. So in this video I will continue on the process flow diagram for liquid extraction. Okay, so this is a schematic diagram to show the process flow diagram for the liquid extraction process. Okay, so this is very different, quite different with distillation process. Okay, 1, 2, 3 and n, this is showing the number of stages. Okay, the number of stages in the liquid extraction process. Okay, but I will show you the single stage first. Okay, so this is the single stage. If I have a single stage liquid LLE process, so this is how the flow diagram will be. So the feed we will denote as L node. So the raffinate we denote as Ln. Okay, at the upper part, which is the feed for the solvent, we put Vn plus 1, and the extract product we denote as V1. Okay, so the V1 L node, Vn plus 1 and Ln will be the same for the multi-stage LLE process. Okay, so this is for the single stage. Okay, so for single stage, usually feed will enter the process. It will have component A and B. Okay, so we also consider C, but usually C is 0 during the feed. So C is representing the solvent. Okay, so A and B will have the value of the composition. Okay, so okay, let's see Vn plus 1. Okay, for Vn plus 1, we also considering A, B and C, component A, B and C, but usually solvent will enter the system as a pure component. So A and B is 0 while C is 1. Okay, so meaning that solvent is purely is a pure component. It has only one types of component. Okay, but usually in liquid extraction system, even though we know that solvent is a pure solvent, it doesn't have A and B, component A and B, but we considering also A and B, but we put 0. Okay, so the same thing will goes for Ln and Vn plus 1. So Ln also have component A, B and C, while V1 also have component A, B and C. Okay, so in liquid extraction system, we will consider three types of component. Okay, so it has a three component system. A and B comes from the mixture, and C is the solvent. Okay, so when the feed and the Vn plus 1, which is the solvent, it will mix here and it will generate two types of product, extract and raffinate. So both extract and raffinate, when the solvent mix with the feed containing component A and B, so the product, either it is raffinate or extract, it will has three components. Okay, means B1 it will have A value, B value and C value, and for the raffinate it has A, B and C value. Okay, just for Ln and Vn plus 1, L node, it only has component A and B. We put C as 0, and Vn plus 1, it only has C, and we put 1. A and B is 0. Okay, so this is for the single stage. Now I'm going to draw for the multi-stage. Okay, so for multi-stage, let's say I have a 1, 2, 3 and n. So as my number of stages. So the feed will be the same, which is L0, and here you can draw like this, and the raffinate we will put Ln. Okay, so this one we will put Vn plus 1 as the solvent. Okay, so this will be V1. Okay, so you can see that the symbol now it makes sense. Okay, so L0 means that liquid or the feed comes from stage 0. Okay, so Ln means the liquid comes from stage n, so we put Ln. Okay, so after n is n plus 1, so solvent we put Vn plus 1 because of it comes from Vn plus 1 stage. Okay, so and V1 means it comes from the stage 1, so we put V1. Okay, so this is for the multi-stage. So if I put L0 here, so means here is L1, here is L2, here is L3, and this is Ln. Okay, so this one will be Vn, V3, V2, and V1. So you can see that it is actually starting to make sense. Okay, so the symbol is showing that the stream comes from which stage. Okay, so this will be the flow diagram for the multi-stage of LLE process. Okay, so another thing is when we in LLE extraction process, we want to know how much component A has been removed or has been extracted by the solvent. So we will calculate the percentage of A being removed by using this equation. So L0 x A0. Okay, so you can see here L0 x A0, you times and you minus with Ln x xn1, so Ln xn. Okay, and you divide by L0 x A0. Okay, so means component A here you minus with the component A here, and you divide by the component A in the feed. So you will get how much percentage A has been removed. Okay, and you times with 100. So I think that one is very easy. Okay, now I'm going to explain on the graphical method of the liquid extraction process. Okay, so as I mentioned just now, in LLE the system actually composed of 3 substances. Okay, so 3 substances it will appear, okay, in both raffinate and extract product. Okay, so if I can draw for you here, so this is the feed, we put L0, this is the raffinate Ln, so this is Vn plus 1, the solvent, and the extract we put as V1. So all the system we have 3 components. We are considering 3 components: A, B, and C. A, B, and C. A, B, and C. Even though we know that during in the feed L0 we don't have C actually, and in the solvent A, if the solvent is a pure solvent, so A and B doesn't exist, only C has the value. Okay, so but for the product extract and raffinate, we have 3 types of component. We have 3 substances. Okay, so that's why the sentence or the statement say that the system composed of at least 3 substances, and generally all 3 components appear at least to some extent in both phases. So these 3 components we can represent in terms of graphical method. So we have 2 types of graphical. So first is the right triangular diagram. So this is right triangular diagram, and we have equilateral triangular diagram. We have 2 types of diagram. So I will explain what are the differences between these 2 diagrams. Okay, so let's look at the I think we go to equilateral triangular diagram first. Okay, so this is equilateral triangular diagram. So first I wanted to show you. So there is a triangular big outside, and there is equilateral triangular inside. Okay, you can see the triangular, isn't it? So in this triangular we have 3 sides. Okay, so you can see this side, so this side, and this side. Okay, so these 3 sides representing the 3 components. So let's say I have a fit. I have a component A and B. Here I have component A, B, C. This one is solvent, so usually I have component C, and here is the extract. I have A, B, and C. So you can see that at least I have 3 components in this LLE system. So I will present the 3 components into the equilateral triangular diagram. Okay, so let's say I have component A and B. I want to separate A from B, and I will use C as a solvent. So C will extract A will dissolve into C, and B will leave as a residual. Okay, so in this system we have, as you can see, in this system we have 3 sides representing the 3 components. So you can see that here we have water as a component A, ethylene glycol as a component B, and furfural as a component C. Okay, so you can put these three components at any side. Okay, so this is all depends on you. But in this system, the water is being set at this side, ethylene glycol at this side, and furfural at this side. Okay, how can I know water, which axis representing water and which axis representing ethylene glycol? So I can see here, if you can see here, this is 10, 20, 30, 40, 15, 16, 17, 18, and 19, and this is water. So the increasing number of the increasing number here from 10 to 19, so they put here water. So this is actually representing water axis. Okay, so for this side 10 until 19, it put ethylene glycol. So this will be the axis for ethylene glycol. And this side from 10 to 90, it put furfural as component C. So this is the component for the this is axis for furfural. Okay, so you can see this on the label. Okay, and you can see also we have also equilibrium curve inside the triangle. So this is the equilibrium curve. Okay, so I will explain later how we can construct the equilibrium curve. Okay, and we also have the dotted line here is the tie line. Okay, so this is the tie line. Okay, and what else? Okay, okay, let's see how to put, let's say I have, when I mix the feed and the solvent, okay, so when the, if I can draw here, okay, so this is feed L naught, and I will put also the solvent Vn plus 1. Okay, so this will be mixed, feed containing component A and B, while the solvent consists of component C. It will mix together, so it will form an intermediate. We call it as M, intermediate. Okay, so before they separate, they form an intermediate phase first. Okay, so when they form the intermediate phase M, so M will have 3 components because of it mixed. A, B and C has been mixed, so M will has 3 components, A, B and C. Then M will further separated later. Okay, so M will has 3 components, so A, B and C. Let's say I have M, it has a component A, B and C. A is 0.4, B is 0.3, C is 0.3. Okay, so all, when we sum up this component, we end up, you will get 1. Okay, because of this comes as a fraction. So how can I locate this composition inside this triangular diagram? Okay, so you can start with component A first. A is 0.4, so you go to axis for component A, 0.4, so 0.4 here. So this is the line. Okay, so next B is 0.3, so you go to B axis, 0.3 here, 0.3, so this is the axis, and C is 0.3, so you go to the axis of 4C, so you find 0.3, so this is the axis for 0.3. Okay, so this is the coordinate for M. Okay, so this is how we locate the composition fraction inside the triangular diagram. Okay, so in this system also, inside any point inside the equilibrium curve, we call it as 2 liquid phase, because of in this equilibrium curve, what happen is the feed and the solvent will be mixed. So feed is a liquid and Vn plus 1 is a liquid also. So 2 liquid, it will mix together. So that's why we call it as 2 liquid phases. Okay, outside the equilibrium curve, we call it as a 1 liquid phases. Okay, so let's say I have a L naught, I mix it with Vn plus 1, okay, as a solvent. So L naught, the coordinate, usually the mixture, it has a A and B, while Vn plus 1, it has C only. So the coordinate for L naught usually will be outside here. So it means that it haven't mixed yet. Okay, it contains 1 liquid phase. Either it is feed or it is a solvent. So when these two mix together, so the location of the M or the mixture will be inside the equilibrium curve. So which means it has a 2 liquid phases. So this is another way. Okay, so how to locate the mass fraction of the 3 components inside the triangular diagram. Okay, let's say I have XA. Okay, so XA is 0.35, you put 0.35. Okay, and for XB, 0.25, you go to B axis and you find 0.25, and C is 0.4, and so this is the coordinate. Okay, so this will be the coordinate. Okay, so this is another diagram. We call it right triangular diagram. Okay, so this is diagram which is different from the equitable triangular diagram. Okay, so in right triangular diagram we only have two components. Okay, so just now in equilateral we can locate the position or the three component mass fraction inside the diagram, but in right triangular diagram we only involve two components. Okay, let's say I have M here, I have 0.4, 0.3, 0.3. Let's say, okay, as an example, the coordinate that we can put in right triangular diagram only component A and C. Okay, so we don't bother about B, we only considering A and C. So inside this triangular diagram, right triangular diagram, the y-axis is a component C and the x-axis is a component A. Component A. Okay, so let's say I have 0.4 and 0.3, so you put 0.4 and 0.3 here, let's see. So this coordinate of M. Okay, just like that. Okay, so in right triangular diagram we also have the equilibrium curve. So the curve is the equilibrium curve, and inside the equilibrium curve also we call it as two-phase region, same like the equilateral triangular diagram. Okay, and outside the curve is, we call it one-phase region. Okay, so the dotted line also we call it as tie line. Okay, seems like seems like the other diagram that I explained just now. Okay, but for right triangular diagram we have another graph at the bottom. Okay, so this will be the 45-degree line. Okay, so this is the equilibrium curve. Okay, so we will use two types of graph. Okay, so whereas the graph at the top is we call it as mass fraction A and C, and at the below we call it as water layer of the raffinate composition. Okay, so here is the bottom graph is displaying the extract and also the raffinate composition. So we will use both graph in order to get how much extract and how much composition of raffinate. Okay, so we will use two types of graph. Okay, at the top and at the bottom. Okay, later I will show you. So okay, in both graph, either it is right triangular or the equilateral triangular diagram, we have equilibrium curve, isn't it? So how to construct the equilibrium curve? Okay, so if we have three types of component, so this, let's say, okay, this is component A, B and C, A, B and C. Okay, so for the data, the equilibrium data, so we have two types of layer, which is the water layer and isopropyl ether layer. Okay, what is this layer? If I can draw for you, let's say I have a pit L node, I have component A and B. Okay, so this is the solvent Bn plus 1, so it only has component C. Okay, so this is the extract product, we call it as B1. It will has A, B and C. And let me erase this one. And this will be the raffinate, or we call it as L1, and it has component A, B and C. Okay, so the water layer, let's say A is acetic acid, and B is water, and my solvent is isopropyl ether. I put ether. Okay, so water layer means we don't want water, so water will exit as L1 as a raffinate. Okay, so when we call it, when the water layer means here is the raffinate here. This is water layer. Because of we don't want water, so we will remove the water at the raffinate. So this is what we call water layer or raffinate layer. Okay, so the isopropyl ether layer means at the top. So here ether or the solvent will extract the acetate and will exit the system as B1 or as the extract product. Okay, B1. So it will reach with ether here. So we extract the isopropyl ether layer is actually the extract layer. Okay, where the product which has reached in solvent ether. Okay, product which reach in the residual, we call it as raffinate layer. Okay, so water layer is actually raffinate layer, and the isopropyl ether is actually the extract layer. Okay, so you will be provided with this data. Okay, so what you should do is you only need the coordinate. Let's say this is for rectangular diagram. Okay, so rectangular diagram only you only have to plot component C versus component A. So you don't bother about B. So you take A and C. Okay, let's say raffinate layer, A and C 0 and 0.012, 0.012. So you locate 0.12 here, 0.0 here. Okay, until you get 0.464, 0.464 here, and 0.165 here. Okay, so here is actually the coordinate for this one, and we call it as a raffinate layer. This is raffinate, coordinate for raffinate. Okay, and for the extract layer, you will do the same thing. Okay, you don't bother about B. You only take component A and C. So component A and C, you plot the coordinate. Okay, I think it will start from here, 0.3. Sorry, it will end here. Okay, you will start here and it will end here. So 0.362, the last coordinate will be here. So you join all the dot, the point, and you join from the, this is what we call extract layer. And this extract layer, you will join this the final coordinate with the final coordinate of raffinate, and you will join both, and you will get a curve, a complete curve. Okay, so this equilibrium curve actually is combination of the extract and also the raffinate layer. Okay, so this is how we construct the equilibrium curve. The same thing will goes for the equilateral triangular system. Okay. Okay. So the same thing. Okay, what is tie line? Okay, so tie line is actually a pair of abstract and refinite coordinate. Okay, so a pair means if you have the first coordinate, as I mentioned, this is the abstract layer, this is the refinite layer. Okay, refinite layer. So the refinite and abstract, the first coordinate of the abstract you will match with the first coordinate of refinite, so you will get a tie line. Okay, so this is, we call it as tie line. Okay, so tie line, and you will construct the tie line of each of the coordinate. Okay, so means this coordinate it will match with this coordinate and so on. Okay, until the last coordinate. So that's what we call tie line. Okay, that's all. Thank you.